And then the acetate, I'm sorry, not the acetate, the acetic acid, H, C2H3O2. And I want a one direction arrow. That's it. You can't even hear that without smiling, can you?
No, I can't.
I say that for you, Chinook.
Chinook's not even here. Wait, where is he? Oh, Chinook!
Oh, I knew where you were.
Oh, he's in the back.
How did you?
Okay, now, what is it? Beneath, what are you doing?
Oh, okay.
What is going to happen when this strong base reacts with this acid?
Water and
Neutralization, that's right. This thing is a very strong acid or base. It's going to take the hydrogen away and make H2O plus the acetate ion. If we want to know how many moles of NaOH, we need quantities here in this problem. Can we use stoichiometry, or is this an equilibrium kind of problem?
Stoichiometry.
It's a stoichiometry because it's a one-direction reaction. We use ice tables and equilibrium when we have just like a weak acid sitting in water or whatever, a weak acid and its conjugate base mixed together. Because they don't really react with each other, they're just both there. But there is a reaction going on here. So we know how many moles of the acetic acid because it tells us there's 1 liter of 2 molarity, so it's 2 moles. So I'm going to put that up here, 2 moles. How many moles of the hydroxide?
Unknown, we need to find
That's
it.
what it's asking for.
X.
We don't know how much, so we'll call it X. Now, how many moles of acetate ion are we starting with?
0.
Yeah, it doesn't say that there's any sodium acetate or any acetate ion at all. So that term is 0. That means that as this reaction proceeds to the right, because it's one direction, it's going to go to completion. The big thing about this problem is knowing which one is the limiting reagent. Which one runs out first?
OH.
How do you know the OH must run out first? Go ahead.
Because halfway point means that there's still going to be acetic acid left. And there's going to be just as much as that as the CH3O2. Yes.
In all cases, I know you're talking about one of these, that one right there, but what about these two?
Oh, it's because it's still acidic, which means that there's...
It's buffered.
Oh, I mean buffered.
You're right, you are right. But I just want to draw your attention to this. Anytime a problem talks about a buffer, that means you have to have acid and base. You have to both. So, this one must be the one to run out first, so that you're left with some of that acid and you're left with base. Are you with me?
Yep.
Mm-hmm.
Buffered. You have to have acid and base both. If this one runs out, then I don't have a buffer.
But what if
Oh.
that runs out and the other one runs out?
That one will be buffered. It can't run out. Okay? So that means this must run out. It's going to go to 0. Therefore, what is the final number of moles of the acetic acid?
1.
No. 2 minus X.
Oh, okay.
And you're talking about part A. I know what you're doing. And then that one goes to just X. So now, because all 3 of these are buffered, that means for all 3 of them, you're going to use the buffer equation. pH, which is given to you, equals pKa plus log of the base, which is that, over the acid, which is that.
That's not actually that bad, is it?
At this point, it's easy. But coming up with that, that's what gives people trouble. Even the chemical equation's not given, so you have to come up with the equation. And we don't overlook the equation. That's one of the hardest things to do for all of these, is to figure out what's doing what and what's happening with in a chemical equation. How do you write the chemical equation? Yes?
That's the whole equation for all A, B, and C.
Yes. Use this for A, B, and C. Yep. So if the pH equals the pKa, that means those just cancel out. And that means log of that equals 0. What point in the titration is that? Not in the titration, but in
Halfway.
the process. It's the halfway point. That means x equals 2 minus x. You solve for x, pretty easy. In part B, they want a pH of 4. So you make that 4. You know the pKa because you know what acid it is. You look up in the back of the book when it's Ka, find pKa. So you know this thing. 4.74 for acetic acid. And then you just solve for x. But getting to this point is not easy. I'm not going to stand up here and say, oh, what's the matter with you? You couldn't get this one? This is hard.
You wouldn't be a good teacher if you said that.
Yeah, I probably wouldn't be. Can I just mention one other thing? Does anybody have any other comments or questions? Anna?
No.
Okay. What are you doing? Oh, I didn't know if you were reminding me of something. Oh, I just wanted to make sure I wasn't missing something. Yes?
Is it 1.8 times 10 to the negative fifth or sixth for acetic acid?
Negative fifth.
Okay.
I wanted to mention something about that graph that I showed you before. I just want to mention this. And I know that we just got done talking about this, but I think it warrants repeating. And it'll do you well to listen to this. If we assume these are all 10s, like this, we see the equivalence point happens at 40 ml. Back at 20 ml, which is half of the volume to get the equivalence point, remember what was significant about that halfway point? Yes, that means that that number right there is the pKa of that acid. So if I were giving you this graph and I said, this is some unknown acid, would you be able to identify what acid it was?
Yeah.
If you give us a table.
If I gave you a table of
Yeah,
Kas, which
then
you
yeah.
had your book, I think that's good to know because what was happening next week? A lab.
Oh. Oh,
What
wow.
if there's an unknown acid in the lab?
What if we go on, like,
That's all I have to say about that.
unknown acid? Is it a common acid or not?
No, I said what I need to say, that's all. Yes, ma'am?
For the PKA, we apply
You can go ahead and
All right.
Thank you.